Hello, I'm Jeffrey Fox again. We're doing big data applications and analytics. We're on the last unit of the cloud computing discussion, and this unit's devoted to data systems and data applications. And we're doing the final set of general access patterns coming from Bob Marcus. We covered the remaining ones in the previous two lessons. So this defines this particular lesson. And it describes, as the previous interaction patterns do, in how users and data interact with the system to give some driving motivations for the system architecture. So here we have an example that's generalized later on of visualizing data. So you have your data storage, which might be constructed in the ways we discussed earlier on. We have your analysis programs. You have an analysis step, and then you have an interactive visualization step. If you happen to listen to some earlier aspects of this particular course, PlotViz will be one of the things you could do interactive visualization with. And this type of pipeline with an orchestration, which provides the interactive software with the right file format, is how we do it ourselves. So you specify which analytics you want, your clustering or your nearest neighbor collaborative filtering, and then you look at the results, and possibly you even cycle back here and rerun the analytics. So this is a very common aspect of whether not only in business but also in science of how you look at data. Because unless you do visualization, there's not much you can do about it. I mean, the eye is so good at picking out things. And visualization also, in some sense, includes looking at printouts. It doesn't have to actually be a picture. All right, so here we have a rather different, somewhat simpler concept. We have our data sitting in HBase and HDFS. And it's actually, of course, got loaded in these ways we've seen before. We mess around with it with Hadoop and Spark and Giraffe, and then we store it in an enterprise data warehouse. And of course, the enterprise data warehouse could have actually supplied the data, which went to here and then got messed around with and then got sent back. And of course, our distinguished person making decisions, possibly in this particular example, actually going to the enterprise data warehouse on the refined data, which got processed by Hadoop, and doing a classic enterprise warehouse type query, typically in SQL. Here's an example of this from TERADATA, which is a major traditional database vendor. But like all such people, it has now everything offered. Here we have R, here we have SAS, the standard statistics software, SQL built on MapReduce, Excel, business intelligence, visualization, lots of languages, and they're all integrated together. Everybody has integrated systems. Of course, they're not obviously fully powerful. So here we have Hadoop sitting around here. We have SQL built on Hadoop, and we have all our multimedia, different media of data. So this picture doesn't say an enormous amount, except that it certainly has to do what Bob Marcus said in the previous case, go from an Hadoop platform to an enterprise data warehouse platform, because people want to query the enterprise data warehouse, and that query will include data processed by Hadoop. Here's another example, number 8. And here we're moving data from data stores to archives, possibly with a transformation. So this is not dissimilar to the previous case. The data is roaring around through here, comes to here, processed here, and then gets stuck in an archive. which hopefully is a little better than the file cabinet, which we've denoted it here in a rather cynical fashion. I mean, this is the old world. When your file cabinet, interactive file cabinet runs out, you can't stick it in a box, which you put on top of the wardrobe or in the basement where it gets wet at the last storm. Who knows what happens? So here we go. Here's a more important type of example where you want to combine data from different sources. This is very common. Here we have a cloud database, which could be, for instance, here. And then we have on-premise stores. There's our on-premise data. And then we somehow have to bring all this together and then process it with Hadoop and Spark, Giraffe and Pig, Mahout and R. So it's sort of similar, except it emphasizes that often data is not in the same place. And that is also often not possible to permanently move this data to here because this data is too big. And also you don't really only want to move it to your on-premise data if you're using it a lot. If you're just doing a one-off type comparison of the NIH Cosmic Store of sequences with your own sequences, it's not so clear you really want to move this. On the other hand, it's not so clear that the Cosmic Store has enough bandwidth to it to actually be able to do this very conveniently. So there are lots of challenges here which are not solved because I pointed out a key feature of data is distributed, and that's emphasized in this plot. Distributed data is a challenge with clouds because clouds do very well on data in the cloud. And your distributed data where it's not in the cloud, and that's actually probably the most common case, quite how you cope with that, it's not well understood because in some sense it's not the right model. Clouds are not built around the model of data sitting in a floppy disk in the long tail of scientists' office. So we have to, this is actually a little more modern than probably the most serious problem. At least we moved it to a classic cloud, a different cloud. Here we have a commercial public storage cloud. And here's one example of this, which this actually has the same picture, except it has multiple sources, which is a classic problem with multidisciplinary work. When you have multidisciplinary work, you would tend to take data from lots of sources. If you're doing environmental genomics, you're taking environmental data and genomics data. Here we have a business example, commodities, industry, weather, financial, and they're all integrated together in the cloud to produce some prediction as to what people will do when the weather's bad and things like that, and how much money will they think. Here we have our database and things like that. So this doesn't say an awful lot more than we said before, but it's a good example of a challenge, which is, I say, not really well understood and maybe not understandable, because it says that we're living in a world which is contradictory, because we have clouds and we have classic distributed systems, and quite how that works and how that should be evolved. Whether the distributed systems will move into a cloud or the cloud should embrace the distributed systems is not obvious. Probably what will happen is all of the above. And the last example is a very important example, which is generalizes the visualization example we did early on, where we have multiple analytics, which one step could be visualization, traditionally the last step, but we need to join them all together. This is what Google Cloud Dataflow does. And we have orchestration. Remember, orchestration was the highest level in the Apache HPC ABDS stack. And we, of course, have our processing here. We have our data store here, and this data store has all the same issues we had on previous slides of possibly being distributed. That's not highlighted here. And the diligent analyst has to specify the pipeline, interact to make certain what's going on. If there's an abort or some problem in the pipeline, then hopefully what they'd love to do is just interact with this step, make a decision, and then say probably rerun more data, etc., and make great decisions make their enterprise do better and better and better. And this handles not only, this issue is true in science as well as commercially. And here is a HORTONWORKS example, which uses, points out that here we have HDFS, we're assuming, which is never true in science, everything is stored in HDFS. Here we have YARN, which has been carefully abstracted from Hadoop so that you can integrate lots of things together. And here we have all our nifty Hadoop capabilities, which all need to be linked together in this type of orchestration to produce a wonderful example. For instance, we might want to take streaming data and join it with SQL database data, which are possibly accessed by high-level scripts and so on, or running iterative MapReduce, or doing a search and so on. This is implicitly has issues of the architecture of the last diagram, but remember those interaction diagrams are just components of a system. Actually, a real system would not only have item 10, they might all have orchestration, but they also have some or many of the previous interaction issues built into them, because they'll have enterprise data warehouses, and they'll have batch data coming from the field, and they'll have purely streaming data. They all need to be integrated together, and that integration requires orchestration and different programs to run in a coherent fashion. So that's the end of this discussion, and the end of our discussion of Bob Marcus's brilliant 10 access patterns, which are very insightful in my opinion. Thank you, Bob.